In the last video, we looked at binary tries in kind of a picturesque form. We talked about their internal structure and how they get laid out in memory. In this video, I want to start writing code that goes with that picture. So I have started some Scala code here. We have a trait for the bvec, that's the name I'm using for our binary trie, based on the Scala vector, which, as I mentioned earlier, is a binary vector. Or a binary trie. I have a colon plus operator. This is the standard operator in Scala for appending to the end of a collection. I have an apply method, the standard method for indexing. This would be get in something like Java. I have an updated method, standard Scala name for what would be set in Java. And I have a size. I am not writing insert or remove because it turns out for this data structure, those operations are very inefficient. These are the things that this is efficient at, and this is where, if you have an application where you're adding things to the end of an immutable collection and you want to index or possibly update things, this is a good collection to do that with. I've declared a companion object here. Now, if you're used to languages like Java, everything that goes in the companion object is the stuff that in Java would have been static. And the first thing in here is a variable I have declared called bits in alphabet. With the code we wrote earlier, I talked about how we could break these up into different sizes, and it impacts how far we have to downshift and the bit mask that we have to use to pull off the appropriate bits. I will write my code so this could be changed from 2 to 4 to 5, whatever, which would allow us to do benchmarking to see what's fastest. But that's not where we're going right now. And then I have an empty, which is defined here to create an empty one of these. So I have a new leaf. There's some details here that I'll mention. They aren't generally important, but these are kind of the right way to do immutable collections in Scala. I have made my type covariant. That the list type in Java, the vector, or in Scala, the vector type in Scala, they're all covariant, and what that affects the subtyping relationships and makes them more flexible, makes them have the behaviors that you kind of expect from collections. It does add a little bit of complexity in our code, though. For example, my append doesn't take an element, it takes something that has to be a supertype of my element. So I've created this type E2, which is a supertype of E. And when we add one of those, it gives us back a bvec of the supertype. Remember that appending does not change the original collection. It doesn't alter what was there. It makes a new collection for you. And so we get back a new collection. What this really allows you to do, so imagine that I had a bvec of apples. I could append a banana to it, and then I would have a bvec of fruit, and Scala would acknowledge that. Similarly, if I do an update and I change one of the apples to be a banana, the result would be a bvec of fruit. It also allows us to pass these into so if I have a function that wants a bvec of fruit, I can pass a bvec of apples into it. If you don't put the plus sign here, you're not allowed to do that. I have two subtypes of this that I mentioned before. I have a leaf and I have an internal, and right now they just have copies of the methods that are not implemented. And so the leaf, as I mentioned in the last video, only has an array of type E. The internal has an array of bvecs, as well as it knows its level in the tree. So the leaves are all at level 0, and then we build up the tree as we add more things. So what I want to do, I guess I should say, I have a test suite here, and I'm a little bit worried about why. Oh, should be, I need to rename this. Okay, and that should make things happy. I have a little test suite here, and if I run the test, it turns out they're going to fail because we haven't written our size method. And so when I try to call size, we're going to have a problem. Okay, so Let's start going through these methods. The first thing that I want to do is an add. You can't do much unless we can actually add to things. And I'm going to start off with just the leaves. And really the right way to approach this is to write the leaves up to the point where you would need an internal and test and make sure that everything works on the leaf, and then start looking at the internal. Actually, I'll go ahead and write size first, mainly because size is remarkably easy. In a lot of our data structures, we make arrays that are oversized because we're going to mutate them. This is an immutable data structure. We're not mutating anything. So the arrays are never bigger than they need to be, which means the size of a leaf is just the amount of data that's in it. That will not be the case for the internal. The internal is a little bit more complex, but for a leaf, that is its size. So how would we add to one of these? Well, if we're starting off with just leaves, then we saw that when I add to a leaf, I basically make a leaf that has an array that's one bigger than what we had before. So I want to make that array. We can start off make array that is one bigger, and then return leaf with that array. Now that works as long as this isn't full. If this were full already, then we wouldn't be able to do that. And I can sketch out what that code is. So first we need to check if we're full. Now, determining whether or not we're full, we need to know how many elements can be represented here. So this would be if the data's length was greater than or equal to the maximum number we can store, which it happens to be that we can calculate this generically by saying 1 upshifted bits in alphabet. So taking a 1 and upshifting it gives you various powers of 2. And so by upshifting it 2, upshifting it 1 goes to 2, upshifting it 2 goes to 4, which is the number of values that we would have. If this, instead of being 2, were 4, this would be 2 to the 4th power, which would be 16. So if our length gets up to that, then we do not produce this new leaf. Instead, we would need to make an internal we also need to make a leaf with one element in it. And actually these need to go in the opposite order. And that internal needs to refer to both the leaf that we added and ourself. This one, the full one, should actually be the first index, and then the internal, or then the new leaf will be the one after it. So we'll come back and we will write that code in in the next video. Right now it's unhappy because I'm not returning anything. But we'll pause here and come back in the next video to actually write this code.